Good morning. Today we are going to finish section 4.1 in AP Calc. And so far we've talked about taking antiderivatives, kind of undoing some of the derivatives that we learned. And just that the process of taking an antiderivative is used to solve what's called a differential equation. Any equation that has a derivative in it, we're going to solve by finding the antiderivative. And today we're going to talk about what's called, as you see here, the particular solution to a differential equation. So let's start where we left off, which was here. General solution. To find the general solution to a differential equation, we would just take the antiderivative. So if f prime of x is 2x, in order to find f of x, it would be the antiderivative of 2x dx. And remember, we're getting comfortable with that notation. That symbol, that's the integration symbol. The dx at the end is just kind of what variable we're with respect to. Again, that'll actually make more sense as we go further on in the chapter. So now I need an antiderivative of 2x. Well, remember we had the power rule I'll write it up here, that the antiderivative or the integral of x to the n, remember we raise the exponent by 1 and we divide it by the new exponent and then put a plus c at the end. So in this case, that x really means x to the first. So officially, this would be, now we might save ourselves a step here, but officially what you're doing here, it would be 2, that's just the constant 2 we're carrying forward, and then it would be x squared over 2. That's raising the exponent by 1 and dividing by the new exponent, plus c, which of course the 2's happen to cancel, which is x squared plus c. There is the general solution to the differential equation f prime of x equals 2x. That means that any function, x squared plus a constant, has the derivative that is 2x. Well, let's look at this graphically. Clearly, you know what x squared looks like. It's just a parabola opening up. And by adding a constant, just moves it up or down. So here I have there are several potential, like what might f of x really equal? Well, it's one of those. It's x squared or x squared plus 1 or x squared plus 2. And I could obviously add any constant or subtract any constant. So what we want to now do is find the particular solution, which means I want to figure out which of those curves is the right curve. And in order to do that, I just need one ordered pair on the graph of f of x. If you give me one ordered pair, I can then figure out which of those curves is correct. And that's what I mean when I mean finding the particular solution. It says if we are given an initial condition, and that's the term, an initial condition, i.e. one ordered pair on the graph of f of x, because I'm missing a parentheses there. We can use that ordered pair to solve for c. Let's figure out what the constant of integration is. And that gives us what's called the particular solution. So we're doing the same process as the other day. We're still finding antiderivatives, and there's going to be a plus c at the end. But after we get there, we're going to use the initial condition to solve for c. All I have left, I have 2 examples, then a short homework assignment. All right, it says solve f prime of x equals 6x, given f of 2 equals 17. My first warning is the fact that they gave us an initial condition, which is this, which means the order pair 2 comma 17 is on my f of x. Understand that we're not going to use that until we take the antiderivative. So we're going to just find f of x, just like we did in the last homework assignment. F of x, that's an f, sorry. That's the integral of 6x dx. That just means the antiderivative. And what is that? So again, we have another example where it's x to the first. That's a 1. So this becomes 6x squared over 2 plus c. And I guess I could clean that up a little bit. 6 over 2 is 3. I get 3x squared plus c. So the general solution is f of x equals 3x squared plus c. But now we are going to use the point, what was it, 217? We're going to use the point 217 to find c. And in particular, that means, so now we've got to be careful what's going to go where. So we're going to put 2 is the x coordinate, it goes there. 17 is the y coordinate, that is f of x, I know you know means y. So this is now going to be, it's going to be 17 equals 3, it was 3x squared, and we gave, the point was 217 plus c. So we are going to replace, substitute 2 for x, 17 for y, and then just solve for c. So this becomes 17 equals 3 times 4 plus c. 17 equals 12 plus c. We subtract 12, we get 5 equals c. We found the constant of integration. It was 5. Don't circle that c equals 5 and tell me you're finished. The particular solution is now f of x equals 3x squared plus 5. That is the particular solution. Sorry, that's messy. The particular solution to that differential equation given that initial condition. Okay, one more, not any more difficult than that one. It says solve y prime equals e to the x given y of 0 equals 3. Now, I'll be honest with you, I don't love this notation, but that still means that the ordered pair 0, 3 is on the graph of the original function. So to find the original function y, we take the integral of e to the x dx. Conveniently, the antiderivative of e to the x is itself. We like that. So y would equal e to the x plus c. And now what? Now we're going to use the point 0, 3. So the 3 is the y, and it's e to the x, which in this case is 0 plus c. Well, e to the 0 is 1, so this becomes, I'll finish this up here. This becomes 3 equals 1 plus c, and I subtract to get c equals 2. So my final answer, my particular solution is y equals e to the x plus 2. That is the function that has two properties. One, its derivative is e to the x, and 2, it goes through the ordered pair, or it satisfies the initial condition that y of 0 equals 3. So that's really it. Although I will say this, in your assignment, there's a couple where it actually gives you the second derivative. And if you take the antiderivative, you get the first derivative, and then there's an initial condition to find c, and then you do the process again to get from the first derivative to the original function. So there are 1, 2, 3 of them, 4 of them, where you'll have to use the process twice, but it's the same process. So that's all I've got. There's your assignment, 287, 38 to 44, and we're good to go. Have a great Friday. See you.